Hello, I am Paras Bedi from IIT Mandi, and in this video we will be discussing about a recent project of mine, that is image classification. In this project we will be doing classification of images from MNIST and CIFAR 10 datasets. Basically, MNIST dataset is a dataset consisting of 70,000 images of handwritten digits in grayscale, and the Sifar-10 dataset is consists of 60,000 RGB images which can be classified into 10 different classes. So in the first part we will be discussing how we can classify the MNIST dataset using multi-layer perceptrons, that is MLPs. So initially we will be using, since we will be using TensorFlow here, so if the TensorFlow is not installed in the the system, we need to install that. After that we will load the required libraries. Further, we will be firstly loading the data and pre-processing it to use for the classification. So firstly we will simply load data using the MNIST class. Then uh, the data consists of total 70,000 images. Each image is of dimensions 28 cross 28 cross 1. That is, there are 28, these are square images of 28 pixels on the x and y axis, and just since it is a grayscale, so there is just a single dimension in the depth field. So the data set is distributed in such a way that 60,000 images are contained in the training data, while there are 10,000 images in the test data. So firstly we will be seeing this only. The training data consists of 60,000 images, each of dimension 28 cross 28. Similarly, the each data each data point has one label, which is just a single dimensional thing. After this, similarly, the test data consists of 10,000 images and so on. So we'll firstly try to visualize the images. So it looks like something like this. Further, now coming to pre-processing this data for training. So since we are using multi-layer perceptrons, we would need to flatten these images once. So the first step would be to flatten the images into a single layer. So is like this is a 28 cross 28 pixel image. We will be using reshaping it into 784, that is 28 into 28 dimensional vector. So each image would be now represented by a 784 dimensional vector, and there are 60,000 such images in the training data and 10,000 in the test data. Similarly, since there are 10 classes, that is the digits from 0 to 9, so we will be converting the data labels into a 10 dimensional vectors. Basically, we will be representing it in the form of one hot encoding. So finally, we will separate the validation data while training from this portion as well, with a train test split of zero point 0.2 test size. So till now we have loaded the images and pre-processed them so that we can begin our training model. To begin with, we will simply use a single layer neural network. Basically, we will be mapping the input layer to a single output layer. In this, we will be creating a sequential model in which we will add a dense layer which will have an activation function of softmax. We will be using softmax since it is a classification purpose. So then we will be compiling the model. SGD we will be using as the optimizer, and cross entropy would be our loss metric. Then we'll be training the model, and we can see on evaluating that we are getting a percentage accuracy of 90.88%. This means that this is a fairly good accuracy since it is a single layer neural network. Now we will try to improve this accuracy as well by by increasing the number of layers, that is by going more deep. So we will be, instead of using a single output layer, we will be introducing an additional additional three hidden layers as well. So these additional layers would be of 500. The first dense layer, hidden dense layer, would consist of 500 perceptrons, second of 100, and third of 50. And initially I have defined the activation function and ReLU for all these, and the final output layer would be having the same dimension as the number of classes, that is 10, and a softmax activation function for classification. We can see here on evaluating that the accuracy comes pretty low, that is 9.79. This is like the model has not learnt anything, because there are 10 classes, and even without learning anything there is a 10% probability that it will predict correctly. So now we will try to figure out what could be the reason of the model unable to learn anything. One possible reason, one possible thing which we can notice is that while training, in every epoch, there is a loss of NaN, that is not a number. This could be a problem, and probably the main reason for this should be some exploding gradients or something like that. So instead of keeping the last layer as ReLU in the third step, we'll be using a sigmoid layer here. The third dense layer would be a sigmoid, and we can see that just by changing this we can achieve a percentage accuracy of 94.04%, which is even more than the single layer perceptron. Now we will try to improve our optimizers as well. So instead of using the normal SGD, we will add SGD with momentum, that is stochastic gradient descent, with a momentum of 0.35. So on doing this we can see the accuracy even increases to 96.72%. Further, we will be using other optimizers like Adam and Adagrad. In Adam, we can see the accuracy is 95.99%, and in Adagrad, the accuracy is 95.89%, which is almost similar to what we were getting using STD with momentum. So we can see that there was a problem of exploding gradients, which was fixed by using sigmoid activation in the last hidden layer. Instead of using sigmoid activation, what we could have additionally done could be normalizing the initial input values. That would have already like uh, improved our initial training model only. So after further improving the optimizers, we saw that an accuracy of 96.5% was obtained. Now we will be trying another thing in this model, that is we will be trying to add dropout regulations. In this, we will be randomly dropping out some of the perceptrons in each hidden layer. On doing this, we can see that the accuracy hasn't improved much, it is still around 96% only, and this indicates that there was no case of overfitting. And it should not be an there should not be any overfitting actually, because the data that we are using for training is 60,000 images, which is quite large. Then coming we can see that a three hidden layer model with SGD with momentum as a optimizer work pretty well for the function. And then we can just look at the summary of this model. We have total of three hidden dense layers, and finally an output layer of 10 dimensions. And then we will be just saving the model. We will be saving the model weights as a .h5 file, and the model structure, that is which layers when we have added, as a JSON file. And we can see, like in my local directory here are the local directory, here are the two saved models. Now we will just try to load the saved model, and looking at the summary, it is the same, that is we have loaded the correct model. And finally the accuracy of 95.89% has been achieved. Now we will try to do the same on Cephire 10 dataset. So in Cephire 10, since it is an RGB image, we will be trying MLP and let's see what happens here. So initially again we will need TensorFlow for this and importing the required libraries. Then we will be loading the data. So the Cephire 10 data set is like we have 60,000 images, out of which 50,000 are training images and 10,000 are test images. Each image is of a dimension of 32 cross 32 cross 3. That is a square image of 32 pixels on x and y sides and a depth of 3, because since these are RGB images, so there are three dimensions corresponding to red, green, and blue values. Now we will be just defining the categories and visualizing some of the images. The images are pretty blurred because the resolution of image is just 32 cross 32, which is quite less. So firstly we will need to process the data. That is, since we will be trying MLP, we will need to flatten these images, and this time we will normalize it initially only, unlike we did in MNIST dataset. And after that we will be using one hot encoding for like converting the uh, labels to 10 dimensional vectors. Then we will be creating a sequential model consisting of three dense layers and a final three hidden dense layers and a final output layer. We will be using SGD with momentum as the optimizer and cross entropy loss. Then we will be training the model, and let's visualize the training process. So these are the model loss. We can see the loss decreasing at every epoch and the model accuracy increasing at every epoch. We can see that the accuracy is touching around 50% after like using optimum parameters, and 50% is a fairly good accuracy since these are images, since they are RGB images and we are not using any like we are just flattening the images, we are not even taking into consideration the spatial arrangement. So we will be finally saving this MLP model for Cephire 10 dataset. Now we will be trying, we saw that the accuracy is 50% only, which is fair enough, but we will try to improve this accuracy using CNN, that is convolutional neural networks. So an important feature here is using these convolutional neural networks, we will be taking into account the spatial arrangement like of the pixels. Instead of directly flattening, we will be firstly using this spatial information for training, and then we will flatten and um, just build a neural net. So firstly we will be loading the test and train data, and here we don't need to flatten this, so directly we will normalize this, convert the classes into one hot encoded vectors, and begin a CNN like sequential model. In this sequential model we will firstly add a convolutional layer of 16 filters with a kernel size of 3 and a stride of 1 cross 1. That is, we will be using a 3 cross 3 kernel which would be moving through moving just one pixel each time in each step, and we will be keeping an activation of ReLU, and this 16 filters mean that total we will be using 16 kernel filters, 3 cross 3 kernel like convolution. We will be carrying out this 16 times to get 16 matrices, like 16 depth matrix. Further we will be adding another convolution layer of a uh, similar like structure. Then we will add a third convolutional layer where we will have 32 filters instead of 16, and we will be using a 2 cross 2 stride. Basically we will be moving 2 pixels. So essentially what we are doing is we are convoluting as well as doing some sort of pooling as well. just to decrease the dimensionality. Further, we will be using another convolution layer of 64 filters and same stride, like stride in both the directions. Then, since we have done this convolution part, now we will be adding some dropout layers, flatten the data, and add a dense layer with an activation function of ReLU. And finally, we will be using our output dense layer with an activation function of softmax for classification. The optimizer we will be using would be SGD with the momentum, and finally we will just compile this model, train the model, and then we will try to visualize the training process. This is how the loss is decreasing and how the accuracy is increasing in each epoch. We can see that the validation accuracy plateaus down after a certain time. This might be due to some overfitting. However, we are getting an accuracy of around 70%, which is fair enough and quite an improvement from the previous 50%. Now we will be saving this model as well, and then we will be loading the two models. So summarizing this, what we did, we in the MLP, we took we created three dense layers. The first one with 1024 dimensional vectors, then 256 dimensions, and the third dense layer of 32 dimensions. And finally we will be having a output dense layer of 10 dimension for 10 classes. And what we had in the CNN, we had three convolution layers, and further we flattened the data, and then we used a single dense layer, and finally an output layer. So we will test these loaded models now. On testing, we can see that the percentage accuracy of MLP on the test data comes 48.83%, while for CNN it comes 67.27%. So we can conclude that using the CNN, we can improve the accuracy by a great amount, and this accuracy can be further improved by reducing some overfitting in the CNN, which might be some case here, and further we can use more advanced techniques as well, which are available these days. Thank you.